Good evening, children. Today I am going to teach you on the chapter of energy. Before we go to energy, we need to know what is work done. What is work? Work is said to be done if the force applied on a body moves it. If no motion takes place, no work is done. So in order to do work, force will have to be applied on a body, and there should be distance or displacement moved by a body. Otherwise, no work is done. Here are a few examples of the work done. We see here these two people, they push each one of them a body. Okay, when we say a body in a chapter of physics, it can be anything that has mass. Okay, so this person is pushing this and it's moving in this direction by some displacement or distance, and this person is pushing another body in opposite direction and it has displacement as well. Similarly, we see this person climbing the ladder. Okay, so in climbing the ladder, work is done against gravity because he's going up. Similarly, this person who is climbing the stairs, he is also doing work against gravity. And here is a person who is pushing a body with a force of 10 Newton, and the body gets displaced by 2 meters. Alright, so from here up to here. So these are examples of work done. No work is done with no change in position of the body. Meaning, when there is no change in the position of the body, even when force is applied, there will be no work done. So a person does no work if there is no change in position or no motion even after the application of the force. Which means when force is applied on a body and there is no change at all in its position, even when we apply the force, that means there is no motion at all in a body after applying the force, then no work is done. So here we see two persons, they are pushing a wall, but they could not move it. There is no displacement. When we apply the force and the force is acting upon the object, but does not cause any displacement or no distance moved by the object, then work is not done. Work is done by a force if the force applied on a body changes its shape or size. Here is a force applied upon this body, which is rectangular in shape, and we find when we apply the force on it, it changes its shape. Okay, so when we apply the force on an object, all right, it could be also from different directions. If it changes the shape or the size of the body, then work is said to be done by a force upon a body. Conditions for work to be done. The following are the conditions for work to be done. Number one, the force must act on a body. Do you see the word must? That means it's compulsory that the force act on a body. Otherwise, no work will be done. Two, the force must produce change in position. There has to be a change in position from one to the other. That is motion of the body or change in size or shape of the body. When force is applied, then there has to be a change. Either there will be motion or there will be a change in shape or size of the body. Then only we say that the work is done. Factors affecting the amount of work done. The amount of work done by a force depends on the following two factors. One, the magnitude of the force applied. The word magnitude means how big, how small is the force, okay? So the magnitude of the force applied. Work done is more if the force applied to move a body is more. Meaning, when the force is more, work done will also be more. 2. The distance moved by the body in the direction of the force. Work done is more if the distance moved by the body in the direction of the force is more. Please pay attention carefully here. When force is applied on a body, then a body will move. Which direction will the body move? It will move in the direction of the force. Okay? So when it moves in the direction of the force, more is the distance moved by it in the direction of the force, then more work is done. Measurement of work done. The work done by a force on a body is equal to the product of the force applied and the distance moved by the body in the direction of the force, which means work done is equal to force into the distance moved in the direction of the force. So when we push a body, here is a force applied, okay, so upon this body, and from this point a body moves here. So it moves in the direction of the force, all right? So the work done here is measured by force into, this is distance or displacement. So work done is equal to force into distance or displacement. Units of work. Work done is equal to force into displacement or distance. This is the relation that we had seen just now, okay? Based on this, in order to get the SI unit of work done, remember we need to go to the unit of force. SI unit of force is Newton, in full, all small letters, symbol capital N, okay? Then SI unit of distance or displacement is meter, symbol small m. Hence, SI unit of work done equals Newton into meter, okay? Newton into meter. Newton into meter is known as joule. When you write it in full, it's all with small letters. Please don't write capital J, okay? But if you take the symbol only, then it will be 1 capital J. Therefore, in 1 joule, we have 1 Newton into 1 meter, which means it's equal to 1 Newton meter. Symbolically, if we write it it will be 1 joule or 1 J equals 1 capital N into 1 meter. Alright. So from here we can define joule. What is 1 joule? 1 joule of work is said to be done if 1 Newton force, when acting on a body, moves it by 1 meter in the direction of the force. Alright? Is the work done when 1 Newton force, when acting upon a body, moves the body by 1 meter in its own direction, meaning in the direction of the force. Alright? Then the bigger units of work which are commonly used are kilojoule. This is a symbol, kJ. Then megajoule, mj, where 1 kilojoule is equal to 1000 joule. Remember children, last time I had mentioned it, kilo means 1000 times, alright? So kilojoule means 1000 joule, and we can write it in terms of the standard notation 10 to the power 3 joule. Then 1 megajoule is equal to 1 million joule, and in standard notation it's equal to 10 to the power 6 joule. Other unit of work is kgf into meter, and 1 kgf into meter is equal to 9.8 joule. Okay, please remember the relationship with joule. Alright, then we go to energy. What is energy? Energy is the capacity of doing work. Okay? Capacity of doing work is called energy. There is a close relation between work and energy. Alright? So this is the relationship. Okay. When you run around the field, you feel tired. The reason is because a lot of energy is spent in doing work by you. To do more amount of work, we need to spend more energy. Hence, there is a direct relationship between work and energy. Now, please listen carefully to this. How much energy you have inside, nobody can measure it, alright? But we measure it in terms of the work that you do. Okay? So we can measure how much is the distance that you run. So that becomes your work done. And in doing that work, you spend energy. So the energy usually is to be given by someone, or it's there with you and you are giving it. Alright? And in order to know how much is the energy spent or the energy supplied, we measure it in terms of the work done. Okay? So, work and energy has a direct relationship. This is important. You feel tired when you spend energy. And why do you spend it? Because you are doing work. Alright? Similarly, the work done on a body in changing its state is said to be the energy possessed by a body. And children, I want you to learn carefully the spelling of the word possessed. because many times I find that the children wrote this spelling wrongly. Please learn it carefully, all right? Then we go to the unit of energy. Since work and energy are closely related, energy is measured in the same unit as work. So, SI unit of energy is joule, just like work done, all right? But when we define joule in terms of energy, we have to mention as the energy, all right? A body is said to possess an energy of 1 joule if it can do 1 joule work, or if 1 joule work is done on it. Here is a slight difference. In this case, either work is done by a body or something else is doing work on a body. So we have to say if it can do 1 joule work or if 1 joule work is done on it. We go to mechanical energy. What is mechanical energy? The energy possessed by a body due to its state of rest or state of motion is called mechanical energy. Okay, please remember, state of rest or state of motion, all right? So the energy possessed by the body in these two states, state of rest or state of motion, is called mechanical energy. And in fact, the sum total of potential energy and kinetic energy is known as mechanical energy. I'm going to discuss with you about these two forms of mechanical energy. So mechanical energy is of 2 forms. 1, potential energy. 2, kinetic energy. What is potential energy? The energy possessed by a body due to its state of rest or position is called potential energy. Please mark the difference here. State of rest, we did not say or state of motion, but we say or position. Okay? That means both will be in the state of rest, but this one could be at a position, which we are going to discuss again shortly. This type of energy is known as potential energy. Potential energy can be A, elastic potential energy, and 2, gravitational potential energy. Elastic potential energy. What is elastic potential energy? The energy stored in a body. Okay, this is stored inside a body. When work is done on it by a force to bring it to the state of rest. Remember, we have always mentioned that in order to bring the change in the state of a body, there should be force applied, okay? So in order to make a body to come to the state of rest, there must have been a force acting upon it to bring it to that state of rest. So there is work done by a force to bring it to the state of rest. As a result, it has that energy stored inside it. Then gravitational potential energy. The energy stored in a body when it is taken to a height against the force of gravity is called the gravitational potential energy. and its symbol is capital U. Now, just remember, when we define potential energy, we say in the state of rest or position. Why position? That means a body must have been taken to a height, okay? So when a body is taken to a height, then there is a force acting on it, and hence work is done in taking it up against the force of gravity which acts vertically down. Okay? As a result, because it is in a high position up at a height, hence we have the force of the work done against the force of gravity. All right? So a body will have that energy which is stored inside when work is done against gravity by a force, all right, in taking it up. As a result, this energy which is stored inside a body when it's taken to a height is called the gravitational potential energy. So due to position, why? Because it is at a height. Okay, so that is a position. Gravitational potential energy is equal to M into G into H, or U equals mgh. Very important relationship. Please remember it. All right. What is m? Where m equals the mass of the body, g equals acceleration due to gravity, and h is equal to the height of the body. So, gravitational potential energy is measured in terms of this relation. Here are a few examples that you see. Okay. Look at this body. It's a brick which is at a height. Because of its position in this height, okay, it possesses gravitational potential energy. Then we see here a bow with an arrow, okay, in a stretch form. We have a bow with an arrow. So in this stretch form, the arrow is not released yet. So this body will have potential energy. Okay. In this case, it's not gravitational, it's elastic potential energy. And if you look at these stones, these are also present at a height. So because they are at a position at a certain height, so these stones will possess potential energy which is gravitational, all right? It's gravitational potential energy. And here we have a compressed spring. In this form, when it is compressed, before you release your hand, in this form, a spring possesses elastic potential energy. And if you look at this catapult, which is stretched along with a stone and the stone is not yet released, this is also a form of elastic potential energy. Expression for gravitational potential energy is PE, which is the short form for potential energy, or U, all right, equals mgh. This is known as the expression for gravitational potential energy. The SI unit of potential energy is joule because it is a form of energy. Then the factors affecting potential energy. Please learn the factors carefully, all right? Potential energy depends on the following factors. 1. Mass of the body. Do you see here we have the mass? Mass of the body. Greater the mass of the body, greater the potential energy of the body. Okay. The next is the height, because G will not change at the same place. All right. It will change only from in different places. So if you are measuring in the same place, G is the same. So it's constant. But height can change. Height above the ground. From where do we measure the height? It's from the ground. Okay. So we have to mention height above the ground, not simply height. More the height of the body, greater is the potential energy of the body. So if you look at this diagram, one body is at a lower height and another body is at a higher height. Hence, the gravitational potential energy of this body in blue, all right, will be more than the body in red because it is at a higher height. Then we go to the second form of mechanical energy, which is known as kinetic energy, with the symbol Ke. The energy possessed by the body due to its state of motion is called kinetic energy. Alright, so when a body is in motion, it possesses kinetic energy. The factors affecting kinetic energy. The kinetic energy depends on the following two factors. A. Mass of the body. Greater the mass of the body, higher is its kinetic energy. Then next, the speed of the body. Not the height anymore, it's the speed of the body because it's moving. More is the speed of the body, higher is the kinetic energy. Okay, and kinetic energy has this expression. Ke, which means kinetic energy, equals half mv square, where m is the mass of the body and v is the velocity, or we can say the speed of the body. Okay, so we have the mass of the body and the speed of the body. All right. So when mass is more, kinetic energy will be more. When the speed or the velocity is more, kinetic energy will be more. All right. The SI unit of kinetic energy is joule because it's a form of energy. Then conversion of potential energy into kinetic energy. The potential energy changes into kinetic energy when it is put to use. Okay, when you use the potential energy, then it changes into kinetic energy. Now, in absence of friction, the sum of potential energy and kinetic energy remains constant, which means if there is no friction, if you add potential energy and kinetic energy, it will remain the same at any instant. All right, but if there is friction, it changes. All right, that's why we say in absence of friction, the sum of potential and kinetic energy remains constant. This is called the law of conservation of energy. Okay, So let's have some examples which I have given here. This is the example. Do you see this girl? She is holding a ball. And this ball, because it is high up to a height, the girl is to a height. So this ball possesses potential energy. Now this girl releases this ball. As soon as she releases it, then the ball comes into motion, all right? And when it comes to motion, then it moves. And when it moves, the potential energy that is present here now is converted into kinetic energy. Now let's take a look at this, all right? Here we have a pulley, all right? And it's a heavy weight that is present here. And we want to pull something up. So what do? This weight now is released and dropped down. When you drop it down, this weight will come to the ground, and while it moves here, as it moves, it pulls the weight up, up, up till it comes up. All right. So what do we see? When you use this potential energy of this small machine here, from here you drop it down, then it does work by pulling the weight up. So what do we have? Potential energy here, which is possessed by this machine. Now when you make it to move, it does work, all right? And it makes this to come up. It's not only changing into kinetic energy, but it does work as well. Now, let's take back a bow and arrow, which we have discussed before. Now, in the stretch form, this bow, which is along with the arrow here, in the stretched form, it possesses potential energy. Now, as soon as you release it, then the arrow will also move. So what happens? The arrow in motion can do work. So it's not only moving, but it can also do work. Okay? Then we have a simple pendulum. Now a simple pendulum, when it is at rest here in the middle, it possesses potential energy. Now you'll have to pull it a little bit to the side. See here, we pull it to the side, and in pulling it to the side, someone is doing work on a simple pendulum. So on releasing it now, this pendulum will move. Okay, it will move from here to here. Now what happens? Over here, while it is at rest, it possesses potential energy. As soon as it comes into motion, that potential energy changes into kinetic energy. And when it reaches this point, all potential energy from here has changed into kinetic energy totally. Then it moves again. It does not stop here. It comes here. And as it comes here, momentarily it stops. So that kinetic energy that it possesses here will change back into potential energy. And then it moves again. And as it moves, it possesses kinetic energy. Totally, the potential energy will become kinetic when it reaches this point. And then that kinetic energy, when it comes here, will change back into potential energy. So we see the change from potential to kinetic, from kinetic to potential, back again from potential to kinetic, kinetic to potential, all right? So in a simple pendulum, the change from potential and kinetic energy comes in its oscillation. The next example is this toy over here. This toy rests at a height, so it possesses potential energy. Okay? Now, as soon as this is released, okay, it moves, it comes into motion. When it comes into motion, that potential energy is now converted into kinetic energy. And because of this velocity of the body, then it moves, keeps on moving along this path, okay? So here we see the change from potential to kinetic energy. Then this is a rolling object, okay? As the object is high up here, it will possess potential energy. Now, if you release it, it rolls, rolls, rolls. As it rolls, the height will become, remember the height is measured from the ground, so the height will be reduced, 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 till it comes to the ground where the height will become 0. So what happened? From potential energy that it has from here, now as it moves, it possesses kinetic energy, and when it reaches the ground, potential energy will become 0. Alright, just at the point when it touches the ground, the potential energy will become 0. Alright, it will all be converted into kinetic energy. Okay, so we have the transformation of energy. Now, please keep in mind, children, in daily life, we are using many different forms of energy. Energy cannot be destroyed, nor can it be created. It can only be transformed from one form to another. So we are using many devices at home, okay? And in using these devices, as soon as you use it, there is transformation of energy. Alright? Transformation of energy from one form to the other form. So here are some devices. The moment you use these devices, you put them into use, then there will be transformation of energy. So we have electric generator. When you use electric generator, mechanical energy is transformed to electrical energy. Then electric motor, it transforms electrical energy to mechanical energy. Then toaster, oven, heater, geyser, we use them in daily life, okay? Then we have the transformation of energy from electrical energy to heat energy. Then electric bell, transformation of energy is from electrical energy to sound energy. A microphone, it transforms sound energy to electrical energy, and this is in the form of electrical signals. Then sunlight, light energy is transformed to chemical energy by green plants. Then electric bulb, there are 2 steps of transformation here. The electrical energy first transforms to heat energy, then to light energy. Then photoelectric cell, okay, light energy to electrical energy. Steam engine, chemical energy to mechanical energy. Moving parts of machine, mechanical energy to heat energy. Alright, this heat is coming because in the moving parts of machine, there will always be friction. And when friction arises, heat energy will come in. Alright? So we have mechanical energy in the moving parts to be transformed to heat energy. Then power. What is power? The power of a body is defined as the rate of doing work by the body. Okay? So, if a body performs a work W in time T, the power spent by the body is power equals work done by the body divided by time taken. Now, please remember, children, when we use the word rate, it means divided by something, all right? And work done changes with time. So the work done by the time taken to do that work. Otherwise, we can also say it work done in 1 second, all right? So that is known as the power of a body, all right? Or we can write it symbolically, P equals W by T, all right? I mark this equation as equation 1 because it's from here that we will get the unit. The unit, all right? From this relation, look, here we have work done, here we have time. So, SI unit of power is, unit of work is joule, unit of time, SI unit is second. So we have joule per second, all right? We say joule per second. And joule per second is known as what? W-A-T-T, all small when you write in full and capital W when you write it symbolically. What is 1 watt? 1 watt is the power spent when 1 joule of work is done in 1 second. All right, 1 joule of work is done in 1 second. We say the power spent is 1 watt. Bigger units are kilowatt. We write it 1 kW, which is equal to 10 to the power 3 watt. Then we have megawatt, all right, or 1 MW equals 10 to the power 6 watt. The factors affecting power of a source. Now, the power of a source depends upon these 2 factors. 1, the work done by a source. More is the work done, more will be the power. Okay, I repeat, more is the work done, more will be the power. The time taken by the source to do the work. In this case, less time taken, more will be the power of a source. Less time is taken, then more will be the power of a source. Thank you.